Hello, I'm Amir Yakhtin, the CEO of Shiraz Rail Transportation Organization in Iran, and I'm pleased to share important project in our city with you. In this video, our aim is to take you through the construction process of the link and the crossover tunnels of Shiraz Metro Line 2. We'll explore the details of tunnel construction, the challenges we faced, and the creative solutions we developed. In this section, we'll introduce the key stakeholders of our project, each playing a crucial role in its success.
Client: the Shiraz municipality, specifically its subordinate, the Shiraz Rail Transportation Organization, is responsible for funding and commission the project after construction. Consultant: the Pajuhes consultant engineers provide design oversight and technical planning for the project. Construction contractor: Rahab Company specializes in infrastructure projects, handling excavation and construction tasks.
In this presentation, we will talk about the following topics. At the beginning, we will take a look at the project's history and the reasons for its construction. Following that, we will look at design and construction process as well as the challenges we encountered along the way. Finally, we will address the project's schedule, budget, and safety status.
Shiraz, the city where our project is located, is a place steeped in history and culture. It's in the southwest of Iran and is known for its historical buildings that reflect its ancient past. Shiraz is also famous for being the hometown of Iranian poets like Hafez and Sadi. Today, it's a lively city with a diverse and hospitable population of around 2 million, making it the fourth largest city in Iran. To address the problem of traffic congestion in Shiraz and help improve the air quality, especially during the colder months of the year, the development of metro lines has been a part of the city's plans for past 10 years. The Shiraz metro network and its lines, after those in the capital city Tehran, are the second largest metro system in the country. Once completed, it's expected to support over 200 million trips annually. The first line of the Shiraz Metro, which is 24.5 kilometers long, connects the eastern and western areas of the city, serving as a vital link within Shiraz. This line includes 20 passenger stations. During peak hours, Shiraz Metro's Line 1 transports 600,000 passengers daily. The second line of the Shiraz Metro is approximately 15 kilometers long, with 13 passenger stations, extends from the southern to the northern parts of the city, providing service to important historical and cultural landmarks such as Hafez Tomb, Sadi Tomb, and Shiraz University of Medical Sciences. Line 2 also connects densely populated areas of the city to modern commercial hubs. Studies show that the construction and operation of this line have led to a 5% reduction in pollutant emission, a 4% decrease in fuel consumption, and a 7% reduction in non-public vehicle traffic. Travel times have also been reduced by approximately 12%.
Project consists of two important parts, the link tunnel and the crossover tunnel, each serving specific roles within the Shiraz metro system. The link tunnel is designed to make it easy for trains to move between Line 1 and Line 2.
This tunnel is about 237 meters long, 8 meters wide, and 6 meters in height. The crossover tunnel is a key component of the metro network. allowing trains to switch tracks to go in the opposite direction in Line 2. The overall length of crossover is about 95 meters and consists of 3 sections. The most critical is about 28 meters in width, 12 meters in height, with 17 meters soil on the crown. Building these structures enables train exchanges between Line 1 and the new Line 2. They also support Line 2's urgent operation, given the incomplete train parking facilities. The project was initially budgeted at approximately 6.5 million euros and was estimated to be completed in 24 months. The excavation volume carried out in the link tunnel was approximately 15,000 cubic meters, and in the crossover zone was about 18,000 cubic meters. The design process, considering stakeholder expectations and numerical modeling, took into account the ground traffic, the population, and building density in the project area. Due to these factors, the new Austrian tunneling method, NATM, was selected as the underground excavation method for this project. This method also enabled the preservation of the sole green space in this densely urbanized area, covering an area of 20,000 square meters. 2- and 3-dimensional analysis was conducted to assess the stability and design of both temporary and final structures. The aim of this modeling was to investigate settlement in surface structures, overall stability of excavation sections, and to explore possible measures for reducing settlement in subsequent stages. In general, the following steps were carried out for the excavation and construction of crossover. Installation of forepoling for initial reinforcement at the crown of the section. Excavation of the upper area and installation of temporary structures. Removal of existing segmental tunnel sections. Excavation of the lower area and installation of temporary structures. Execution of a portion final lining, including approximately half of foundation and wall. Completion of excavation for all sections and finalizing the main structure's ring. The first challenges of project was access to the starting point of the cross-structure excavation. Due to the presence of green spaces at ground level and existing military zones, it was not possible to construct a vertical shaft for commencing the excavation. The only available means of access to the initial section of the crossover tunnel was through the link tunnel. As a result, a cross-cut structure was employed to provide sufficient space to commence the excavation of the crossover. To achieve this, we required a 3-way structure. This structure not only allowed uninterrupted access for the excavation of the crossover structure, but also facilitated the transfer of loads from the temporary structure over the segmental tunnel sections onto the ground. The existing segmental tunnels also needed to be demolished to gain access to the starting section of the excavation. Since the demolition of the segmental tunnel took place from the outside, there was a risk of overall instability in the tunnel section. To mitigate this risk, temporary support columns were installed within these tunnels to facilitate the demolition process. Adjacent segments were also securely connected from the inside using metal plates.
The presence of underground water at the base of the tunnel walls, loose soil within the tunnel's cross section, and the large size of the excavation section led to project delays and posed safety risks to the excavation process.
To control groundwater seepage and stabilize the surrounding soil, injection was employed. The forepoling system was also used to enhance stability in the crown and sidewalls of the sections. Based on previous computer analysis, forepoling systems with a length of 6 meters and a spacing of 1.5 meters were employed. Furthermore, based on lessons learned from past projects, an unexcavated wedge-shaped area was left in each phase to ensure stability of excavation phase.
Before commencing the excavation, a comprehensive assessment of the surface level structures, generally around 70 years old with vulnerable steel frameworks, was conducted. The condition of these structures was evaluated using a questionnaire known as BCS forms. They consider their overall health based on visual observation and existing technical documentation.
Based on BCS forms ranking, additional instrumentation was installed on some of these structures. These instruments were monitored, and the status of these structures was observed on a daily basis. Another challenge was the ground settlement, which exceeded the computational predictions in one of the sections. Based on a pre-designed scenario in the project's risk analysis, double-layer initial support had been used to control this settlement. Safety in the project is assessed using the Frequency Severity Index (FSI). The maximum recorded FSI in this project was 0.06, indicating a relatively low number and severity of safety incidents. Continuous monitoring and analysis of safety data during the construction process helped identify potential hazards, leading to swift actions to mitigate their effects. A key focus of this project was the proactive control of schedule deviations. Based on lessons learned from previous project and stakeholders' requirements, WBS and critical path of project was determined. Detailed reports were regularly generated on a daily, weekly, and monthly basis to monitor progress. This approach has resulted in the project's Schedule Performance Index, SPI, falling within the acceptable range of 0.75 to 0.95. Furthermore, the Schedule Variance, SV, has been effectively managed, maintaining minimal values close to zero. The initial estimated budget for the project was 6.5 million euros, and effective cost control measures ensured that the Cost Performance Index, CPI, was maintained around 1.
In conclusion, this project marked a significant milestone in our area. It showcases our team's dedication, expertise, and unwavering commitment to safety, quality, and efficiency, signifying a remarkable advancement in local and national engineering experience. We look forward to a brighter future with improved transportation and opportunities for all. Thank you for your attention.